Hello everybody, welcome to this video. I'm Hao. In this video, I will present our paper entitled Lightweight Post-Quantum Encapsulation for 8-bit AVR Microcontrollers. This is a joint work with Johann, Peter, and Peter. The Ericsson Mobility Report of this year showed the total number of IoT connections is expected to reach more than 24 billion in 2025. It is increasing with a compound annual growth rate of 15%. As the IoT application market is widening, more advanced use cases are emerging, and it spurs the research on the more advanced IoT technologies. Especially, it demands lightweight cryptographic schemes and protocols for the IoT security concerns. The 8-bit AVR architecture serves as a good example for a hardware platform for many IoT applications such as wireless sensor nodes, smart cars, and so on. The AVR architecture is based on the RISC philosophy and modified Harvard memory model. It comes with 32 8-bit general-purpose working registers, and each AVR instruction has a fixed latency. For example, the bitwise logical instructions and most arithmetic instructions like addition or subtraction take 1 clock cycle. By contrast, the multiplication and RAM accessing instructions have the cost of 2 clock cycles. I suppose almost everyone here has heard about quantum computing. The quantum computing is treated as subversive technology in the domain of cryptography. It makes use of quantum mechanical phenomena such as superposition and entanglement, allowing it to solve certain hard problems efficiently. Especially, Shor's algorithm provided the theoretic foundations for quantum computers to solve integer factorization problem and discrete logarithm problem in polynomial time. It is generally believed that a large-scale quantum computer would be able to break essentially most public key crypto systems used today, in particular RSA and ECC, which based on these two hard problems. The threat posed by quantum computing has aroused a large body of research in post-quantum cryptography. It is a relatively new subfield of cryptology that is intractable for quantum computers. In 2016, NIST initiated a process to solicit, evaluate, and standardize one or more quantum-resistant PQC algorithms. It claims to consider the performance of candidates not only on the high-end processors, but also on the resource-constrained devices. And so far, it has come to the third round. Among the NIST candidates, the lattice-based cryptosystems are considered the most promising candidates for deployment in constrained devices because of their relatively cheap computational cost and small keys and ciphertexts. The benchmarking results collected in the course of the PQM4 project showed most of the lattice-based encapsulation mechanisms are faster than Curve 25519 key exchange protocol on the ARM Cortex-M4 platform. However, the results of PQM4 also indicate the lattice-based cryptosystems generally require a large amount of runtime memory, usually between 5 kilobytes and 30 kilobytes. For comparison, a variable-based scale multiplication on Curve 25519 can have a RAM footprint of less than 500 bytes. So one may argue that PQM4 implementations have been optimized to reach high speed rather than low memory consumption. But this argument is not convincing, since even a conventional implementation of Curve 25519 still needs a RAM usage of only little more than 500 bytes. The high RAM requirement of lattice-based crypto systems pose a serious problem for AVR devices, since AVR microcontrollers feature only a few kilobytes of RAM. For example, a typical wireless sensor node, Maxi mode, comes with only 4 kilobytes internal SRAM. These 4 kilobytes are easily sufficient for curve 25519, but not for the lattice-based crypto systems. As a result, there is a clear need to research how lattice-based crypto systems can be optimized to reduce their memory consumption, and what performance such low memory implementations can reach. The Goldilocks and ThreeBears is a famous British fairy tale, and it's very interesting. It has another version in the domain of cryptography. The designer Mike Hamburg proposed an elliptic curve named ED448 Goldilocks in 2015, and the ECDH key exchange protocol based on this curve has been supported in the TLS 1.3. The designer explained why he called this curve as Goldilocks, because this curve uses a solidness prime for its underlying field, and this form of this solidness prime defined golden ratio. And as similar as original fairy tale, soon after, ThreeBears appeared in front of the Goldilocks. ThreeBears' key-encapsulation mechanism is a second round candidate in the NIST POC Standardization, and unfortunately it was not selected into the third round. This crypto system is named as ThreeBears because the prime for the underlying field is also a golden ratio solidness prime. ThreeBears is a lattice-based crypto system, and its security relies on the integer module learning with arrows problem. ThreeBears has three parameter sets called BabyBear, Mama Bear, and Papa Bear, matching these security categories 2, 4, and 5. So each parameter set comes with two instances providing respectively CPA and CCA security. This paper analyzes the performance of ThreeBears on an 8-bit AVR microcontroller and studies its flexibility to achieve different trade-offs between the RAM footprint and execution time. And what needs to be mentioned here is this work was carried out and submitted before the announcement of the third round candidates of the PQC standardization. In this work, we presented the first highly optimized software implementations of BabyBear for the AVR platform. Our implementations possess constant runtime, and all of the optimization techniques presented here can be directly applied to the Mama Bear and Papa Bear as well. So first, we developed two implementations optimized for the low RAM consumption. One is CCA secure, and the other one is CPA secure. In the specification of ThreeBears, the CCA secure instance is just called BabyBear, and the CPA secure instance is called BabyBear ephemeral. So our implementations are developed based on a low memory implementation in the NIST package. Notably, these two memory optimized BabyBear versions are the most memory efficient implementations of a second round candidate ever reported in the iterator. Additionally, we also developed two implementations optimized for the high speed to research the different trade-offs. These high speed versions are based on the optimized implementation in this package. So totally, there are 4 different implementations in terms of BabyBear. And at the lower level, what we mainly did is we designed a memory optimized Mac operation and a speed optimized Mac operation, respectively for the above memory efficient and high speed versions. Okay, let's turn to the ThreeBears itself. The underlying field of ThreeBears is an integer field that is not like polynomial rings used by other lattice-based crypto systems. So concretely, the prime n is 2 to the power of 3120 minus 2 to the power of 1560 and minus 1. The prime n is also usually written in another 2 different ways as listed. Regarding the field operations, the addition is a conventional modular addition, and the multiplication is slightly special. It requires 2 operands 2 times with a so-called clarifier, which is the multiplicative inverse of the lambda. The purpose of multiplying with this clarifier is to avoid amplifying the noise during the computation. As for the scheme, first, let's see the CCA secure instance. The key generation produces a key pair. The private key is a random string. The public key contains a hash string and a vector. Both of them are derived from the private key. The encapsulation takes a public key and a random string G as input, and it generates the shared secret and ciphertext. The shared secret is just simply obtained by hashing the string R with G. Well, in the decapsulation, it needs to reduce the key generation and encapsulation, and finally output the shared secret by checking if it correctly reproduced the ciphertext. As for the CPAC, for instance, the different parts are highlighted. The encapsulation is just slightly different. The decapsulation removed repeating the key generation and the encapsulation, and by using some hash operations instead. Okay, to summarize it from an implementation viewpoint, the entire scheme mainly consists of two parts. One is auxiliary functions, for example, the samplers and the error correction, and the other one is arithmetic components, especially the MAC operation. Among auxiliary functions, both the noise sampler and the uniform sampler are based on the C-shake, and in essence, it relies on the key check permutation at the lowest level. So we can speed up both samplers by using an open source highly optimized AVR assembler of the key check permutation. Then for the malicious code, the original implementation in the NIST package has small code size and memory requirements and runs in constant time. Moreover, its runtime is almost negligible, so we just use it directly. However, for the arithmetic computations, in particular the MAC operation, it appears several times in all the key generation, the encapsulation, and decapsulation. So from our measurement for the source code of the ThreeBears, the MAC operation actually dominates both the RAM footprint and the execution time. Indeed, it needs a special care. Okay, now in the following, we are going to see how we optimize this MAC operation. We start from the point of the field element representation. The field elements are large integers with a length of 3120 bits. In the NIST package of ThreeBears, all the implementations take advantage of the reduced radix representation for field elements. For example, on the 32-bit platform, each limb is 26 bits long, and the element contains a total of 120 limbs. Because there are 6 free bits in each word, storing the carry bits during arithmetic computations is possible. It is not urgent to propagate the carry instantly. So many computations eliminated the dependency with others. High-end processors could beneficially carry out a few instructions in parallel and save the runtime. However, in our work, we come up with a full radix representation for the field element. Several reasons. First, the AVR processor executes instructions in sequential order. Even there is no dependency among the instructions, it cannot execute them in parallel. Second, using reduced radix representation for 8-bit machine words significantly increases the RAM consumption and requires much more instructions. So we choose full radix representation. And notably, though the register size of AVR is 8-bit, we set the word size in our representation to be 32-bit. Because we will take advantage of so-called RPS multiplication technique, the detail will be presented later. So compared with original reduced radix representation, we find the full radix representation saves 88 bytes for each element. Okay, afterward, let's start analyzing the MAC operation from a mathematical aspect. So first, we know the inverse of lambda equals to lambda minus 1 in this field. We divided each element into the lower half and higher half. Then the field multiplication can be converted this way. And now we apply the Kurzhubel multiplication. So it can be converted to equation 1. Thanks to the special form of the modulus n, equation 1 saves 1 addition compared to the conventional Kurzhubel multiplication. Plus, with the integer r, the MAC operation is shown as equation 2, and it can be transformed into equation 3 and 4. The original low memory implementation in the NIST package developed its MAC operation according to this equation 4. we develop our memory-optimized Mac operation based on the original Mac operation in the NIST package. So here is our memory-optimized Mac operation. There are several differences between our implementation and the original implementation in the NIST package. Since we use full radix representation for operands, we need to add some necessary alignments. Moreover, we use RPS multiplication to further accelerate this Mac operation on AVR. So our Mac implementation actually is using a hybrid multiplication, but the original one uses a pure product scaling multiplication. So only these 80-bit accumulators Z0, Z1, Z2, and several local variables takes actual RAM footprint in our algorithm. And we do not use more levels of Kurzüber multiplication because it will take more RAM consumption. So basically, this Mac has two parts. The former part is main loop of the Mac operation and is highlighted. It makes use of the product scaling multiplication. And the Mac operation is interleaved with modular reduction in each iteration. The rest part contains a final modular reduction and the carry propagation. This part is relatively simple compared to the former part, so we are going to focus on the former part. Of course, from an implementation viewpoint, in a nested loop, the inner loop operations deserve the most attention since they are performed the most frequently. The inner loop operations are called triple Mac here. This triple Mac operation corresponds to 3 multiplications in the equation on the top. The corresponding items are marked with the same colors. Okay, now we are going to analyze in detail this triple Mac operation. As shown in the right figure, the product of two field elements A times B has a double length compared to a single field element. So we split the product into 4 parts and we use 4 accumulators to accumulate this product. Each accumulator manages 1560 bits. The first triple Mac loop is implemented in a straightforward way according to the equation. So instead, performing a subtraction in the inner loop, only after the whole inner loop, D0 will minus the double of D2. This reduces execution time. For the second triple Mac loop, some tricks are applied here. So in the beginning, the original straightforward implementation is shown here. So compared to the first loop, it just simply switched each accumulator to the next. And each multiplication should times with 2 to the power of beta due to the alignment. Since it will not affect your understanding of other parts, so I will not give details about alignment here. However, as mentioned before, the modular reduction is interleaved with Mac operation in each iteration of the main loop. The lambda to the power of 3 will be reduced to 2 times lambda plus 1, so which means that at the end of the iteration, the 0 will add with D3. And actually, Z1 does not need to minus double of D3 after the second inner loop, because it will add another double of D3 at the end. So it means basically, we can remove the operation as a line 8. And we can directly accumulate the value of the third Mac to Z0. As a result, it's possible to remove the D3 and save the RAM consumption caused by Z3. So this is also the reason why we choose equation 4, not 2 or 3, because other equations need more accumulators and take more RAM consumption. So let's finally analyze very basic word level multiplication, for example, AJ times BK. So each word, as we said before, is 32 bits long, which is 4 bytes. The reverse product scaling multiplication is an enhanced variant of the hybrid method designed for the AVR platform. It has several advantages. It's very fast and has small code size and use fewer registers and is parameterized. So finally, we take advantage of the inner loop operations of RPS multiplication to accelerate this 4 times 4 bytes multiplication, so which is shown in the middle of the figure. Because we use RPS technique to accelerate these inner loop operations, as I mentioned before, in essence, our Mac implementation is using the hybrid multiplication, but the original implementation uses product scaling multiplication. Okay, so basically that's all for the memory optimized Mac operation. So after studying the memory efficient implementation, this time we regard the speed as the primary metric for the optimization, because the Mac operation of the optimized implementation in this package is not friendly for AVR to reach the high speed. So this time we developed this speed optimized Mac operation from scratch. Again, first start from the mathematical aspect to analyze this Mac. We further divide each half-size product into two parts. So currently, each item is 1,560 bits long, and it can be transformed into equation 5. So we developed the speed optimized Mac operation according to this equation 5. Generally, a combination of multiplication techniques with subquadratic and quadratic complexity will yield peak performance. So here, we choose the subtractive Kurzüber method for the higher layer and choose RPS multiplication at the lower layer. We conducted experiments using different levels of the Kurzüber method. And finally, we observed the 3-level Kurzüber with RPS multiplication underneath had the best performance across all different combinations. So we use this strategy to implement the speed optimized Mac operation. To summarize our optimization strategies for Mac operation, we developed the memory optimized Mac operation according to equation 4 and take advantage of 1-level Kurzüber and apply the RPS technique to accelerate the triple Mac. For speed optimized Mac operation, we developed it based on the equation 5. This time, according to the result of the experiment, we use 3-level Kurzüber with RPS multiplication underneath. Here is our experimental environment. And for our source code, only the Mac operation and the key check permutation are AVR assemblers. Other components are C code to keep a small code size. So let's see the performance of our software. In our 4 implementations, the high-speed Mac operation is 1.5 times faster at memory-efficient version, and the speed gap between the two different Macs directly affects key generation, encapsulation, and decapsulation's execution time. However, in terms of RAM consumption, the memory-efficient Mac only takes 82 bytes, so that is even below 10% of the high-speed version. And finally, the memory-efficient version is 1.5 times RAM-efficient compared to the high-speed version. And all the implementation had code size of around 11 kilobytes. Compared to the widely used Curve 25519 key exchange protocol, in terms of memory-efficient CPA-secure implementation of BabyBear, the encapsulation is slightly faster, while the decapsulation is even over 4 times faster on AVR. However, the RAM consumption is still much higher, and it needs 1.2 kilobytes more than the Curve 25519. Compared with other second-round candidates, due to very few AVR implementations of these candidates, we also list the benchmark results collected in PQM4. From this comparison, we could find that both our CCA and CPA secure implementations of BabyBear are the most RAM-efficient implementation among all the candidates. So, to summarize our work, we presented the first highly optimized assembler implementation of ThreeBears for the 8-bit AVR architecture. Our simulation results show that even with fixed parameter set like BabyBear, many trade-offs between the execution time and RAM consumption are possible. The memory-optimized CPA-secure version of the BabyBear requires only slightly more than 1.7 kilobytes RAM, so which sets a new record for memory efficiency among all known software implementations of second-round candidates. Due to this low memory footprint, BabyBear fits easily into the SRAM of 8-bit AVR 8 mega microcontrollers. ThreeBears is also very suited to be part of hybrid key agreement protocol because multiple precision integer arithmetic can be shared with the low-level field arithmetic of Curve 25519, thereby reducing the overall code size. For all these reasons, ThreeBears is an excellent candidate for a post-quantum crypto system to secure the Internet of Things. That's it. Thanks for your attention.